Okay, we're very pleased to welcome Mohamed Barakat today for a talk about his categorical computer algebra work. Mohamed, whenever you're ready.
Thank you very much. Thank you very much for the invitation. So today's talk will be about UA algorithms. So we're all doing category theory, so there should be no new vocabulary popping up. It should all be categorical. And the only new vocabulary would just be an interpretation for existing stuff already in category theory. So you should expect a categorical interpretation of this awkward word. So the word UA is German, coming from basic or primitive, and UA algorithm should be something very basic algorithm out which we want to extract other algorithms in a constructive way. So this is joint work with Sebastian Pozor, Kamal Saleh, Fabian Sigraf. So Sebastian is a former PhD student and a former postdoc, and his ideas are floating all over this talk, and we're quite influenced by the stuff he did in his PhD and afterwards. Kamal Saleh finished his PhD in 2022, and Fabian just handed in his thesis, and his work was about developing a category theory compiler. And I talked with some of you about this idea. So let us start with a motivating example that is coming from another area. Actually, this is one of the examples that bootstrapped our interest in this categorical programming. I'm originally coming from homological algebra, so the connecting homomorphism is something that is fundamental in homological algebra, as some of you might know. And here's the statement of this. So I know you're more working in distributive categories, in toposes and stuff like that. So an abelian category is more or less another extreme. So it's more or less a topos, but in the linear world or in the pre-abelian world. So given three composable morphisms, A, B, C, in an abelian category, because abelian categories are in particular pre-additive, so there is a notion of a zero object and a zero morphism, so this relation makes sense. A times B times C equal to 0. And you see that I'm composing in the same convention as the people in topos are doing. I'm just dropping the semicolon, right? So it's really the order in which you read. A, B, C is equal to 0. Okay, and then I'm organizing these three composable morphisms in this funny way, because now I can take the co-kernel of A. So if you're doing distributive categories and topos, you would think of a co-equalizer. So this is the co-equalizer of A with the zero morphism from A to B, and this is called the co-kernel. And because, so the co-kernel fulfills the rule that A times D is equal 0, and you have already another competitive for D, namely BC, because A composed with B composed with C is also equal to 0. So B times C is competing with D, and D is the best morphism. So there is a unique co-kernel lift called E, and from this you take the so-called kernel. So this is something like the equalizer object in the linear case. And then you do the same thing on the other side, so it's fully symmetric. So now you go and compute the kernel of the morphism C, and G is, or A times B is, because of the same relation, is competing with G. So there is a unique kernel lift making this diagram or rectangular commute, and from this you can take the co-kernel, which is then the analogous or the general or a special case of the co-equalizer object. And the statement of the snake lemma is the following: then there exists a natural morphism from the kernel of E to the co-kernel of H. And you see why it's called the snake, because it looks like the snake through the diagram. And the word natural means that it's natural in the setup. So it's natural in A, B, and C, and all their objects. So then you can also compute functorially. So the kernel is functorial. So J is the kernel functorial of D, and K is the kernel functorial of G. And then the statement continues with this J, S, K being an exact sequence. So this means if you compute the homology at this object, it vanishes. So the kernel of S is the image of J, And if you compute the homology at this object, it vanishes. So this means the kernel of K is the image of S. So there are two questions we might ask at least. So does this with mean such that or furthermore? Yeah. And in what sense is this S unique? And it would be wonderful if we could get a construction algorithm. But the goal is to get the construction algorithm as a derived algorithm. So this is why we're searching for so-called UA algorithms, having all these guys as special cases. Okay? So we could answer the above questions if we would have an oracle for computing in free abelian categories. And indeed we have one. So this is part of our software. But just a word of caution. So we will use the software now to do proofs and program extractions from proofs. At the very end, we will do the program extraction. But this software is developed to compute in instances. It's not developed as a proof assistant or as a theorem prover. But because the categorical setup is so clean and we can talk about free instances, we can use the free instances as instances to do proofs and program extractions. Yeah? So there is now no difference between computations and proofs. So let me switch to the software. So is it big enough for everyone? So again, this is the diagram you saw. And I'm searching for my mouse. It's here. I've already loaded this Julia package. It's called cap and homalg. It's just a very thin layer above our software, which is entirely written in GAP. And we have this thin layer to run it in Julia because we want to have access to the Jupyter notebook. That's all. Yeah, but the entirety of software is running in GAP with this thin Julia layer called cap and homalg. Yeah. CAP is an abbreviation for categories, algorithms, and programming. So this is, so you should think of GAP as groups, algorithms, and programming, the language or the computer algebra system in which we decided to implement GAP, which has the historical reason because we started with the project homalg, which is a project about homological algebra. And more or less, we had the same history. So we started same history as the true history. Our interest was homological algebra, and then we figured out we need category theory to organize homological algebra. Yeah. So more or less, we reinvented the theory, but on the computer, the history, but on the computer. So and CAP is the project of the PhD project of Sebastian Pozo and Sebastian Gutsche, and this is now what we're developing our entirety of software in, and homalg is still some part of it, at least, for example, things like the matrix interface we developed in homalg is still part of the software.
Actually, if you don't mind zooming in a click, I think that'll be nicer on the video.
Please?
If you don't mind zooming in a click, that
okay.
actually would be better on the video.
Like this?
Yes. Thank you.
So now I'll load a cap-based package. We have, I think, already 20 of them now. So this one is called functor categories. I've already preloaded this because it takes some time. So now it's loaded. And we start by setting up the context. And the context starts with the quiver. So quivers to categories are like sets to monoids. You generate monoids by sets. You generate categories by quivers. So this is the quiver, which I've just written there. I'm unable to write down the relation. And I'm generating the free category of this quiver. So I'm still unable to dictate the relation that A times B times C equal to 0. So I'm defining the field of rationals, and I'm taking the so-called algebroid of this free algebra. So this is like the group algebra, but now you are on a category. Yeah? So this is the generalization of the monoid algebra or a group algebra. And now in here, this is a pre-additive, even a Q linear category. And now I have what is called a zeromorphism. I don't have a zero object, but a zeromorphism. So now I can take this quotient. Yeah, so it's now.
The zero come from? It's declaring it's an algebroid?
Please?
Where did the zero come from? It's declaring it's an algebroid?
Yeah, the zero comes from because your home sets are all Q vector spaces. So you have in every home set a zero. And once you have a zero object, you will figure out that all of these different zero notions, they coincide. But you see here, I'm skipping and now going to the entire abelian closure. This will be a black box. I can talk more about it at the end of the talk if you have more questions. So this is now the abelian closure of L. So now I have an instance in which I have freeness, abelian freeness based on this basic setup. And this is the setup yeah? Dana?
Every time you are clicking, your software is running?
Yeah. So this is interactive, yeah?
Is it important that you take the quotient by the relation before doing the abelian closure, or could you then?
No, it's not important, but it's much easier for the computations. So computationally much easier if you have the relations already embedded before you take. Yeah. Because in the abelian closure, you can take much more stuff than just such small relations. So we're doing this step by step. So if I would have had a relation, so for example, if I would have had A and A prime both going from A and B, and I want to equate them, I would have done this on the level of F. Yeah, because this is the earliest possible stage in which I can add the relation. Yeah.
And how come we're over Q instead of over G?
Because the modeling of this tower uses a piece of software that is still not working for Q. Still not working for Z, but we have another, so the tower which I will use for the extraction works for Z. So there are 3 models, or at least, we have on the computer. So there are at least 3 models, and this model is the one that just accepts Q for the moment. Yeah. Okay, so now I display A, and you see, interrupt me please at any time. So this is an interactive talk. You see now that 42 primitive operations were used to derive 337 derived operations for this category, which is algorithmically equipped with a homomorphism structure, and the home sets are finitely generated and free, and he already knows this category is constructively abelian with enough projectives. So we don't need the projectives, we just need that it's constructively abelian. So this means you have an additive structure, so you have direct sums. These are very special byproducts. And you have kernels and co-kernels. And the homomorphism theorem is valid. So the homomorphism theorem tells you that the natural map between the kernel of the co-kernel and the co-kernel of the kernel is an isomorphism in the category. So if you just say, I have kernels and co-kernels, you have pre-abelian, and you have this natural morphism. And abelian just means that this natural morphism is an iso.
How would this example change if your quiver had a cycle in it?
No, nothing. So
You could enumerate, you're not enumerating morphisms, you're just...
I can, so if I have a cycle and my home spaces are infinite, then I lose the ability to compute home sets. But I could have a cycle which is still giving me a finite relation. For example, like you would have with the Jordan normal form. You take one cycle, which is x, and then you say x fulfills the minimal polynomial of the matrix. Yeah? So it's a cycle, it's just one loop, but fulfilling the minimal polynomial of the matrix, and you're still in this setup. So where you will have full computability. But this is a good point because for the proof, we will need to be able to compute homomorphisms. For the program extraction afterwards, not anymore. Okay? So, and what is the underlying category? So go here. So the underlying category is indeed the algebroid. So the stuff we started with. And I'm hiding for you at the moment what happened going from the linear closure of the free category of the quiver to the abelian closure. So there is much happening. And this maybe will come later in more detail. So let's start with the Unida lemma. So this means I can import my objects in the quiver all the way up till the abelian closure. So this is the object A, the morphism A, the morphism B, and the morphism C. Yeah, and this means their sources and targets were automatically also upgraded. Yeah, from the quiver up to the... And now you can see that the relation is still valid in the abelian closure. So now A and B and C are now living in capital A in the abelian closure. And now I'm doing I'm redoing the statement of the snake lemma. So I'm computing the co-kernel projection D. Yeah.
So in the when you ran the thing to define this category, it said things like there are 42 primitive operations and there are 337 derived operations.
Yeah.
Or whatever. These are the things in green. Are they
Yeah.
of these
Yeah.
operations?
Yeah.
Okay.
Yeah. Dina?
You outlined the proof for us before, and now you were checking the proof, right?
Yeah, actually, I didn't do any proof. I just wrote the statement.
Well, we believed you.
Yeah, exactly. But now you don't need to believe me because now you'll see the proof. And the proof here is not a proof by proof search, but by a computation. So there is a context which you can create on the computer that makes the proof search obsolete. You can now prove, like in computer algebra, by a computation. And usually you do this in computer algebra for instances of examples. But category theory gives you instances which are free. So this means they oversee all the examples. So this means a calculation there is a proof by nature. Yeah? So now I'm computing the co-kernel co-lift of the precomposition of B and C along A. And then I'm computing the kernel embedding. And then I'm computing the kernel lift. And then I'm computing the co-kernel projection, which is this blue eye. And then I'm asking how many morphisms are there from the target of I to the source of F. So this is not the question we actually are interested in. Now I'm using the property that my abelian category can compute Holmes. And if I press enter, it tells me a row module over Q, so a vector space of rank 0, so of dimension 0. There are no non-trivial morphisms. Of course, you can take the 0 morphism. Yeah?
That's
from the wrong one, yeah, so backwards. Yeah, backwards. Yeah. So now you see there is no natural morphism, otherwise it would appear in the free instance, right? And now you do the correct question. So what is the Holmes structure? And it now gives you, it's a vector space of dimension 1 over Q. And that's it. So we didn't need the exactness properties. You just know you have 1 up to scaling, right? It could be 0, but this is then the trivial case. And you have exactly 1 morphism up to scaling. And then you're free to multiply with the unit in your commutative ring K. If you would have taken Z to start with, then it's just plus minus 1. So up to a sign, it would be unique. Otherwise, just multiplication with any scalar in the field. And now we can even extract it. So S is now the basis of external Hom. And this object is a syntactic object. So this is the proof certificate. Yeah, I'm building it in the syntactic category, which is the abelian closure. Okay, and now we go and compute the kernel and verify that actually the width is a furthermore. Yeah, so let's compute J, and then compute the homology and ask is the homology 0, and it says yes. So we know the homology at this point is 0. And then compute K, so by the functoriality of the co-kernel, compute the homology and check that the homology is 0. Yeah.
What happened to ABC equals 0?
They're used in the construction of S. It was crucially used in the construction of S. Yeah. Very nice. So if you would do that, we can do this maybe in the anytime. So just delete the relation, and you will find no natural morphism from the kernel to this one. Yeah, and of course the entire construction breaks because you already used it in the construction. So I used it to say that I have a co-lift here. I needed that for this E here. I needed that A, B, C is equal to 0. Otherwise, I wouldn't have even started making up my context, building up my context. Okay? So exercise along the same lines, treat spectral sequences of bicomplexes. And if you're more ambitious, treat spectral sequences of filtered complexes. Yeah, you can get the proof, and by the end of the talk, you will see how you get the program extraction. So you don't even need to guess anymore what are these algorithms. Yeah?
Does it show that in certain cases morphisms are computable?
They're always computable. So category theory is actually a programming language. It wasn't perceived as such until people like you and our group view it exactly as a programming language. So all this is computable. So I know that this stuff is usually done in mathematics using highly non-constructive embedding theorems like Fried-Mitchell. Yeah? So you take an abelian category, and for no obvious reason, you embed it non-constructively in a category of modules over some horrible ring, and you take this as the proof. But of course, this is a highly non-constructive proof. But category theory as a theory itself is much more computable. And I think you're doing this, you appreciate this, and we're doing this in the same manner. Okay? So we have a proof by computation of the snake lemma with a certificate. Yes, please.
How important was the use of Q rather than Z?
Please?
How important was the use of Q rather than Z? Is that really?
No, it was completely irrelevant. So it was just one piece of the tower that I was hiding from you is just working for Q. But we have 3 different ways in how to build a tower. And the 2 other ones work well with Z. I just didn't use them.
Okay. And the tower being just the construction of the ultimate.
Of the abelian closure, yeah. So going from the linear closure to the abelian closure. So if you're interested, I can show it to you. So. Yeah, are you? So.
So the end thing you construct, whether you use Q or not, you always construct the same abelian closure, and you're working in the abelian.
They're all isomorphic.
They're all isomorphic.
They're all isomorphic. Yeah. So this is. So A is the abelian closure, and this is the modeling category. So it's just the Fried of the finite completion of the algebroid, and Fried is the co-kernel completion. Yeah. So co-kernel completion is the special case of co-equalizer completion, but it's much easier than the co-equalizer completion. And this was done by Fried at the end of the 60s. So yeah.
And the Fried construction of a free finite completion is just magically abelian. You get.
Yeah, because this guy is abelian. The finite completion of the algebroid is automatically abelian, so this remains abelian. Yeah.
Why did you bother with the co-kernels? Why did you bother with the Fried if it was already abelian?
Yeah, because this is the co-equalizer completion of the co-equalizer completion is not the co-equalizer completion.
Yeah.
Yeah, and the same here. So if you would stop here, you will get an abelian category, but this is not the free abelian on the context. So you have to go one step further. Yeah. So let's get this finite completion. This is called C-breve. So let's extract it. This is the underlying category. And look how it's modeled, and it's modeled as the Copré sheaves. So you see it's modeled on the Copré sheaves of the algebroid, and what are the Copré sheaves? They're the opposite of the functor category. And this functor category, at the moment, it just respects algebroids over fields. This is the only reason. But I will show you maybe, if you're interested, at the end of the talk, other constructions where I'm using Fried and co-Fried and additive closure, and I don't need Q. Yeah?
And the choice of closure you make judiciously according to computational property? Like, are certain theorems easier to prove in one closure?
Yeah, so once you compile them, there is no difference.
There's no, okay.
Almost no difference, yeah. But at the very end, when I show you a proof extraction, I will tell you about the difference between two different models. So the proof extraction, you will see the kernels, the co-kernels are maybe outside and the kernels inside. And if you take the dual version, because the abelian category is, if you dualize it, you get again an abelian category. Unlike topos, you would get there a co-topos, something completely different. So if you would dualize the tower, you will get also a free instance. And there you will see that the role of the kernels and the co-kernels in the program extraction are flipped. And this is a fundamentally different algorithm. Even if you're compiling it, you will see that they're using very different algorithms at the end. Okay, good. So let's go back. So we have a proof by computation of the snake lemma, and S is the certificate. So, but how to build a category constructor abelian closure? And what do we need to extract a construction algorithm for the connecting homomorphism S in any abelian category? So I've constructed it in the free instance, right? But I would love to construct it in any abelian category. So the answer is to build the category constructor abelian closure as a categorical tower of two adjunctions. So this is the abelian closure, and I'm still hiding the details here. So the first step would be to take the additive closure. This is the linear version of taking the coproduct completion. But it turns out that it's simultaneously the coproduct and the product completion, so the so-called direct sum completion or additive closure. And then you take, in one tower, either you take co-fried and then fried, or fried and co-fried. Or what you can do here, as we did, you can start with this, take the co-pre-sheaves and then take the fried. Yeah? So there are multiple ways, and this is why it's ... because it's highly non-unique what you would do here. Okay? So this is implemented in several ways as a tower, but we would like to start even with the quivers, to start the adjunctions at the quivers. So the quivers don't give you two categories, just a category. Starting from here, you have a two category. Yeah, but of course, any category can be viewed trivially as a two category. Yeah? So this is the so-called path category construction. And all the way back, you have underlying, so forgetful functors. Yeah? So the co-unit of such a composed two adjunction will turn out to be the desired UA algorithm, having the snake lemma, spectral sequences, and many more algorithms as special cases. So once you have this on your system, you have all this other stuff as special cases. You just need to instantiate the context, the free constant, and then make a program extraction, and then you will have all these algorithms, less fancy like the snake lemma or fancy like the spectral sequence algorithms.
When you showed some underlying category computation earlier, you weren't computing the U, right? You were saying, what's the thing this is free on?
Mm-hmm.
Right.
Yeah.
So the U is going to have really big quivers.
Yeah, exactly. I'm not interested in you.
Yeah. I guess.
Except, exactly that, yes. Absolutely. So the above tower, so by the way, the unit will play a role. So the unit will play a tiny role at the end. But the main algorithm is the co-unit. So the above tower of categorical constructors is typically composed of several free forgetful two adjunctions between a two category D of categories. We call it doctrine, but you might use doctrine for different purposes. We just call it doctrine not to keep saying a two category of categories. And another category E of categories with more structure. So these could be quivers, these could be then categories, or these categories, these are linear categories or K-linear categories, and so on. Yeah? So you go from less structure D to more structure E. And U is then the underlying or the forgetful functor. So we will next see an instructive example of such a two adjunction. So this is the example for you. Maybe if I give the same talk next week at the math department in Berkeley, I'll change the basic example. So coproducts are generalizations with S of joins in posets. You can safely think of least common multiples. So given M1 till ML, you can think of numbers if you're not firm in category theory. Then C would be the coproduct or the LCM of these numbers, together with so-called injections of cofactors of coproducts. So we call them, this is the name in our system. So I'm just once for this stuff when it appears later that you understand what we mean. So the injections are the iotas. And for any other guy who is competing with my coproduct C, in the sense that it also has morphisms going from M1 till ML, there is a unique universal morphism. So C is the least common multiple. Yeah, for every other multiple, C is dividing C prime. Actually, there is another way which is much nicer to repackage this. So you have the coproduct, but you replace the injection by the so-called component, and now you can see the products in a different light. So you can see this as a bijection between this data going from M1, from MI to C, so L different morphisms, and a unique morphism going from the coproduct to any other object. And this is a much more useful repackaging if you want to use your system as a proof assistant. Much nicer than this, because this is really a rewriting. So you can go from this to that and vice versa. Yeah? Yeah, so actually we discovered this later when we wanted to abuse our computational system as a proof assistant. Yeah? But what I showed you is not a proof assistant. What I showed you is a theorem prover. Yeah? I pressed the button and I had the proof with the certificate. So the question is there a way to package all three algorithms, coproduct, injection, universal, or coproduct, component, and universal, in one algorithm? Yeah? And you will see it will turn out to be just the co-unit of the adjunction. It needs all three algorithms. So a co-Cartesian category is a category with all finite coproducts, and denote by cocart the category of co-Cartesian categories as objects and coproduct preserving functors as morphisms. Nothing new. So there exists a free forgetful 2 adjunction. On the one hand, it's just the underlying category. So this is the forgetful functor. And here we have the finite coproduct completion. And I will not build the finite coproduct completion. I will build the finite strict coproduct completion because this simplifies my model. So actually, I'm interested in the strict co-Cartesian categories. Yeah? So what is the model? So it's built completely syntactically. So the objects are just finite lists in D. You know this better than I do. And the morphisms, so now I have as the sources just lists and the targets just lists. And I have then wiring diagrams that are wiring diagrams of generalized functions because these functions are labeled by morphisms in the category D. Right? So it's exactly like an undergraduate or a freshman would write down a function. The only difference is that these functions are labeled. The arrows are labeled, I'm sorry. The arrows are labeled by morphisms in D. So, and the composition, like you would compose functions, and you compose the labels by composing the morphism, by viewing them as morphisms in D. That's it. So, you know that skeletal fin sets is the finite strict coproduct completion of the terminal category. This means where you have no distinction between these objects. They're all indistinguishable elements. So you can view this as a finite set with indistinguishable elements. So the labeling becomes obsolete and you recover the maps, right? And this means that categorically you invent functions by these adjunctions, by this particular adjunction. Yeah? And maybe in the math talk I will take another example where another adjunction will simply invent matrices. Yeah? When you go to the parallel linear world.
So that's like the free byproduct?
Yeah, the additive closure, yeah. So you go from the K linear categories to the K additive categories, and that's it. And this adjunction really invents data structures like functions or matrices as the solution of this universal problem. Yeah? So for a strict co-Cartesian category E and a functor f from D to U of E, so now you see that I'm strictly typing. Other people would write here from D to E, right? But I'm strictly typing because I want both of them to live in the same doctrine. So I have to forget the extra structure I have for, yeah, for E. So the adjunct functor is then the composition of applying the left adjoint to F and then composing in our common convention. So you read it in this way. You apply this and then this. So you apply the co-unit of the adjunction to E, and then you get the adjunct functor from the finite strict coproduct completion and so on. And people used to write it as a lifting property, but I don't like this because this violates the typing. So I like to really write it as an adjunction. Yeah. So, and what is this adjunct functor doing? It's taking a list, so a syntactic object in the strict coproduct completion. It's applying L of F. This is the first step. And then you apply the co-unit. And the co-unit is now taking the syntax and transforming the syntax into semantics. Right? It's taking this syntactic model and saying, now I am in a category E which knows what coproduct means. Right? So I'm going from my syntactic objects, mapping them to F. Now F can be interpreted because now I'm in E and E has coproducts, so this makes sense. So what to do with morphisms? So first of all, you take you apply F to the wire, right? So this is F of phi I. I forgot to write it here. And then you compose it with the injection into the coproduct object. And remember, this is the F of t by what we. So this is what I have here. Yeah, I could have actually written this also there. Yeah, it's missing. Do this on the slides. So I've already used the coproduct. I'm using the injection, and now I need the universal morphism to have the coproduct object here. And now you see the co-unit is the Wu algorithm evaluating syntax into semantics. So I was now able to repackage all the three algorithms in one algorithm, which is the co-unit. And now you see really a nice interpretation of the co-unit. It's evaluating, taking syntax, evaluating it into semantics.
What exactly do the words syntax and semantics mean?
Please?
What exactly do you mean by syntax and semantics?
So the object D is living in D. Yeah, so this is now this is an object not in D but in the finite strict coproduct. This is a syntactic construction. So this is syntax. And now I apply L of F. This means I am applying F to each component. And now each component becomes interpretable in E. And now this syntactic thing becomes now interpretable as the coproduct. So this is syntax semantics. And I'm doing this in 2 steps. Yeah? And you see the crucial one is this one here. The co-unit. So this is how you compute the adjunct in general. This is the very general formula for the adjunct. Yeah? So at this level, nothing is special. Yeah? So this formula is by definition. Okay? I can pause, by the way, if you... Yeah?
So sort of the crucial requirement that you have a concrete description of this free completion that you can implement, right? Like often you can say that such and such completions exist on the basis of very general principles, but it seems like what's going on here is that you really need to have a good
syntactic free model. Yeah. And here I even have chosen the strict model.
Yeah, you've even chosen
a particular model. So I'm now not in the general adjunction, but in the special adjunction because, yeah. So my theorems will be just confined to the strict case. If I would like to have proofs in a more general setup, then I would need to implement the other one, and then I have to go start with the byproducts and then take care of the bracketing so that my associators are not trivial and so on and so on. Yeah?
Is that computationally feasible after some point to handle all those bracketings, or can you still do it?
Yeah. Even the non-strict, yeah, you can. I'm leaving this as a bachelor thesis for one of the students if he's interested in doing this. So by now, all my associators are identities in this here. So I cannot extract algorithms including associators, which is, of course, a restriction. Yeah.
But you could also use theoretical theorems that say anything that's true in the strict case is true
Exactly.
in the general case.
Exactly. Yeah. But of course, when I want to extract the algorithm and apply it to other I need to know where is the associator because it's disappearing in my code. Yeah. So at some point, I will give it to a student as part of his bachelor thesis to implement the other model. Yeah. So the next step, we're coming closer to poly. So the dual category construction is also a two adjunction on each doctrine. So you go from any doctrine to the so-called co-dual. So you take the opposite category on categories, the opposite functor that goes from the same direction. So if f goes from d to e, the opposite guy f op goes from d op to e op without changing direction. But the co-dual means that you just need to change the direction of the two morphisms, and then everything works. Yeah. So this means you can insert these guys into our towers. I say towers because of lack of space. I drew the tower horizontally and not vertically. So now, this is one important thing for you. Maybe this is not important in the math department, that implementing the opposite requires a lot of metaprogramming. And why is that? Because you are implementing different doctrines all the time, and the code is scattered everywhere. But you want a metaprogramming so that every doctrine that you're implementing knows how to compute its opposite. So this means that you have to design the system very carefully at the beginning, or you have to have a painful redesigning at some moment, so that whenever you define a doctrine, you can get the opposite doctrine without pain. And this requires some magic in metaprogramming. So now you can define the product completion, if it's finite or finite strict or whatever, as the opposite of the coproduct completion of the opposite. And I dropped finite and I dropped strict here, so you can take any flavor you want. And the distributive completion is now the composition of these two. First the coproduct, and then first the product and then the coproduct. I'm writing the circle here I'm now back into the old convention. So first the product, and if you switch these two, you will get the co-distributive completion. Yeah? And poly is then the distributive completion of the terminal category. The poly that I see here. But of course, now you can take the distributive completion and apply it to any category. Yeah? And maybe use that to do some primitive proofs in poly. Yeah? But of course, poly has much more structure because this guy has infinitely more structure. It has all the structure of every category you can think of. And this, of course, radiates to the distributive completion. So I'm not claiming that I can use this in any meaningful way to do theorem proving in poly because of the extra structure in poly. I have to make free instances of these extra structure. Yeah. So what you can do here is you can just use the product and the coproduct structure, which you've just inserted in. There is nothing more. Yeah. Everything else you have to add it to the category literally, or you really go and try to, if you have extra structure on the terminal category, that you inherit it to the other constructions. So this is more or less a summary. The left two adjoint L of D is the free category in E, or of type E, generated by D. The data structure of the free model L of D are purely syntactic. The co-unit evaluates syntax into semantics. And I'm happy about this coincidence because if you take the Cartesian product, the co-unit is also called the evaluation for other reasons. Yeah? So I'm happy about this. So now you have two reasons why you would like the word evaluate. It evaluates in the classical sense of applying a function to an element, but also evaluates in the sense that it takes syntax to semantics, as I was showing in this special example. And the proof is computing in the syntactic model and alongside with the proof certificate. And the evaluation into semantics is the program extraction. So you just take the S and then apply the co-unit to it. And this is our very explicit version of the Curry-Howard correspondence, which tells you that if you're doing constructive mathematics, in theory, you can extract programs from proofs. But if you do this, I know Coq is constructive, and Agda is constructive, Lean is not constructive. But even if you go to Coq and to have a constructive proof, good luck in trying to extract. So I saw some extractions, and I think it needs a lot of work until you can get a good algorithm out of them. But we have also some similar issues here. So having constructed the connecting homomorphism S in the syntactically free model, which is the abelian category of the linear closure of the quiver modulo relations, we can now apply our evaluating co-unit, and we don't need another category. We can just plug in the free model. So we don't need any other category category in the doctrine E. We can just take the free model. Yeah. And now you see that it's L of U of L of D. Yeah, but so what? And to the syntactic S, so apply this to the syntactic S and extract the program, and you see that this program looks like that. And I didn't know this structure before. Yeah, so I have implemented the snake lemma by going to a higher category and doing there some computations and then extracting a certificate that this morphism I have constructed lies in my abelian category, in my underlying abelian category. But this I really saw for the first time after we had this technology. And of course, I don't get this on the nose, but I get also stuff coming from the additive closure, which is part of the tower. But then you can use your system as a proof assistant to show that you can get rid of all the vocabulary coming from the additive closure. And if you look here, you just see you have compositions of morphisms, and you just have all the vocabulary for the kernels and the co-kernels, but you don't see any trace anymore from the additive closure, which is also stunning. Yeah? Although you need it, of course, to get to the abelian closure. And I can show you how this looks like. I didn't extract this, but I extracted this modulo some rewriting rules, which I didn't automate yet. So that's it. Thank you very much for your attention. Yes, please.
So forgive me if I say that by stressing generality here, your motivation has been academic, but do you have some thoughts of how you could apply this kind of programming to a more industrial use?
This is why I'm presenting it here. So I know that you are very much interested in applying all this stuff and much more, of course, to industrial applications, and I'd be very interested. So our software can only ripen and get more solid if we have more different applications. Yeah, and I think some parts of the software are still far from being good or usable or widely usable, but I think the more applications we have in this sense as well, the better the software will come. And we see that we have already side effects for other projects. So whenever I'm doing something for one project, I see now the other project is coming within reach. Yeah. So it's academic in the sense that one of the motivation is that I'm really actively searching for a proof that I cannot find by a typical proof search. And I'm now, I think, one step before that. So hopefully maybe in April I will get my proof just by...
For a proof in some kind of algebraic geometry, in some pure...
Yeah, in that case it's connected to algebraic geometry, but it's poset theory. But I wasn't able to find this proof anywhere, and people circumvent this direct proposition, and there is no proof for it anywhere, and I think it was never formulated like that, so that people are never forced to make a direct proof. And I think this will be part of this. So you saw here enrichments over skeletal fin sets. I told you there are also enrichments over other vector spaces and other abelian categories, but we can also enrich over the true-false category, the interval category. So we can also make proofs in posets and lattice theory and so on. Yeah?
First, just a comment, I think this is really lovely work. People often say, like, or frame things as, you start with some sort of logic and do proofs and then try to extract programs from that, but we've sort of turned that viewpoint on its head by saying that we can center computation, and when you specialize computation to a free model, then that actually is giving you a proof. I think that's just a beautiful point of view.
Yeah.
So now an actual question. So you're working with doctrines, and doctrines are often kind of known when you see one kind of concept, and people have tried to formalize it in different ways. I mean, in our work, we've worked with GATs, and more recently we're also experimenting with a double categorical framework for doctrines. But I'm sort of wondering, in working with these different doctrines, do you have an overarching sort of meta system, or are you circumventing the need for that through some other way of structuring your programs?
So the way how we build the doctrine is more ad hoc. Mm-hmm. So the way how we build the doctrine is going and identifying these algorithms like coproduct, injection, and so on, writing the documentation, doing the magic so that the meta programs can take the duals, so the opposite construction, and that's for us a doctrine, basically. So we don't have an underlying system.
Computing the free
and then, and I package so the whole knowledge is in the free.
Yeah, that's the key
aspect
of doctrine that you need.
Exactly. The two adjunction. So the whole knowledge is in the two adjunction, and all the morphisms are packaged inside the co-unit.
And so to repeat, this is done in an ad hoc way, where you need to find a clever syntactic construction of a free thing.
Yes.
And then you can instantiate that doctrine.
Yes. Absolutely. Yeah. Dana?
In old-fashioned recursive function theory, we discovered that certain problems are non-computable. Yeah. Do you have some negative results?
There are, of course, stuff that is not computable. I mean, if you would start with a presentation like this for just a group, and so this could be a finitely presented group, and then you bump into the word problem immediately. Yeah. So you don't have algorithm to decide the equality of morphisms, and a lot of stuff breaks. But the nice thing is that there is still a lot where things are decidable. Yeah. So I find this as more or less type theory on steroids. So you can do much more than you could get from a type system. And somehow this is, for us, replacing a type theoretic system. Yeah? Yeah, please.
Yes, speaking of type systems, so you lived in a Abelian world mainly today. If you would think about the free forgetful two adjunctions for LCCCs or for toposes, this is constructing like the free divided type theory or the free intuitionist.
Exactly.
Can you do any of those?
Pauli was the example. So I had mixed the two worlds. The motivation is the historical motivation with the snake lemma and the spectral sequences. So spectral sequences was my first goal. Yeah. And if you're interested, I can show you how I use them to simplify differential equations.
So you had free distributed.
Yeah.
But that, I guess, is still a ways below, say, like the free topo.
so the free topos on one object would just need to take this guy and take the co-equalizer completion, and I'm working on this.
Okay.
So maybe if I have this, I could give a talk on your colloquium.
Is that a general description of the free topos, the co-equalizer of the free
No,
distributed?
no. The general description is no. So the general description is you have to take the co-limit, so everything finite, yeah. So completion of the limit completion of your diagram that you start with. Yeah, and what happened here, there are several instances. So I start with the one object category, right? So this here is something that you can factorize. This is the equalizer completion of the product completion of D. And you see here, the product completion, so this here gives you a bool, I think, fin bool. And if you factorize this, this gives you co-equalizer completion of the co-product.
Sorry, what is fin bool?
The opposite of fin sets, finite Boolean algebras.
Okay.
So this is co-product completion. So this gives you fin bool, this gives you poly. So up till here you get poly. And with this, if you start with the terminal category, yeah? And here you would get the free elementary topos on the one object category, so the terminal category. And if you start with the initial, then this product completion will give you the terminal. This will give you nothing. So this will give you fin sets, and this will give you, again, fin sets. Yeah, so there is no difference between this and this if you start with the initial one. But this is the general construction. So I showed you today the co-product completion. This is immediate by metaprogramming. So I need this, and this is immediate by metaprogramming. So I'm working on this now, on the co-equalizer completion, which is the nonlinear version of fried. And this is not as simple. And you might bump there in non-decidability issues. I'm not sure yet.
So it's not really in the literature, because the free abelian category, there are many papers on.
So I say that category theorists were programming, but they were not perceiving this as programming. So it might be somewhere. I don't know. Yeah, I mean, we had all this stuff in the abelian world, and then we saw all this organization that is already in the literature. So we discovered the fried construction late, although we have more or less discovered it by doing, you know.
Okay, let's thank our speaker again.